This is a kind of neat thing called the grand jeté, which is this idea that you can even do it with a hammer. We have a hammer here that if you've got a center of mass, like right there, so right now the gravitational torque around my finger is 0 because it's as if gravity is reaching right here, sort of halfway. There's even a dot that someone's measured there. And then if this becomes a projectile, I throw it through the air, for example, it turns out the center of mass is what follows that parabolic trajectory. Okay, so if you're going to use all those equations of kinematics and things that we learned before, this 9.8 meters per second squared, it all applies to the center of mass as the rest of the object might be changing its shape or just rotating, for example. Now a human can actually change their shape, and if a ballet dancer jumps, well, as soon as they leave the floor, by the laws of physics, their center of mass has to do parabolic trajectory. Okay, and we're all used to looking at this. When someone jumps, they go up and they come back down again. But with the ballet dancer, what they do is they do the splits in midair as they're going up, and then the splits come back down, and as a result of that, they actually get their center of mass to go up and down, but their head just goes straight sideways. So you can see like their feet are not touching the ground, but you just see them kind of gliding along as if they're weightless. And so it's this weird move when you watch the ballet dancer do that. You're like, whoa, they just floated. But it's just a trick. Oh yeah, so and the idea is I'm gonna go over some static equilibrium, center of mass. I'm going to talk some more about review today. That's the next 3 things we have to do. We good? Yeah, let's start with learning catalytics, and if you give me a minute, I'll set this up. You won't see it in your phone quite yet. What does it imply if the torque of a 10 Newton force is 0? What does that mean? Does that mean that the force is being applied at the axis of rotation? Does it mean that a line parallel to the, let's just see if we can deliver it here. Rotation. Parallel to the force and passing through the place where the force is exerted passes through the axis of rotation? Yes, sir. Or is it not possible for a 10 Newton force to produce 0 torque? Oh, yeah, so A is right. It is true that if the force is exerted at the axis of rotation, you do get 0 torque. So this is when L equals 0. But this is actually when this L times sine theta equals 0. It's a little more general. Okay, there's 2 ways that L can be 0. That the torque can be 0 if you've got a 10 Newton force. You can either put the 10 newtons right there, 10 newtons, or you could put the 10 newtons way over here at the other side, but you could direct it towards the axis. That's also got a 0 torque. Okay. So I guess, and in both cases actually, the line parallel to the force passes through the axis of rotation. So I'd just say it's a little more general of a result to say it's B. You guys get it? It's like a logic thing. I've said that the torque is 0. What does that imply? It implies, it could imply, I guess, that the force is exerted at the axis of rotation, but not necessarily. Okay? But it definitely does imply that the line parallel to the force passes through the axis of rotation. Okay. I don't know if we can analogize that. Okay, I can't think of an analogy. Should we do an equilibrium problem, static equilibrium problem? Try this out. Anybody have any questions before we progress along here? Sometimes it's easiest to learn this stuff by actually trying a problem. Questions? Thoughts? anyone's having a conversation with their neighbor, could you just ask me the question? So I'm interested to know what people are talking about. Good? So this is from the book. This is the idea of you have an arm, you're holding a ball. When you hold a ball in your hand, then how is that really working? How can you pull upwards on it? Well, what's happening is that you've got biceps and triceps, and both of those they attach to your forearm, and they allow that forearm to rotate around the rotation axis, which is right around here. It's that elbow joint, okay? So torques are happening in your body all the time. If you want to rotate the other way around, like if you flip your hand over and you're trying to push down on a desk, that's again your triceps pulling. So what muscles do is that some sort of electrical impulse goes in there, and these cells want to contract, and they produce this pulling motion. Pulling force, and the pulling force exerts torques on things. So once you've got some sort of a static situation, I'm going to call it isometric, but just when you're holding something still, like holding a ball, you can use these equations of equilibrium to allow you to estimate these muscle tension forces. So the example problem here is saying this. You've got a 6 kilogram lead ball in your hand, like this. So there's a couple things going on here. One is that the force of the ball on the hand is down. Oh, sorry, wrong. What's going on here? There's a downward force of what? I'm getting screwed up. I think there's a downward force on the ball. What is it? What's exerting a downward force on the ball? It's not the hand. Anybody know? Yeah, if you said it, you have to say it again because I didn't hear.
Gravity.
Yeah, I think it's gravity. Yeah, thank you. Earth. Earth, yeah. Earth on the ball. Right, so it's gravity. So the hand is exerting upward force like this, okay, on the ball. Oh yeah, that's what I was going to say. This is the force of and that's equal to mg. The force of the hand on the ball is equal to mg. To cancel that out. So what that means is that there's a force of the ball on the hand, which is down, and is equal to mg. Does that make sense? I don't know how there ended up being 3 of these. The F of the ball on the hand. I know this is overly complicating things, but let me go through that again. First, gravity tries to pull the ball down. So your hand pushes upward on the ball to cancel the gravity. But there's an equal and opposite force of the ball pushing downwards in your hand, and that's trying to rotate your hand that way. So what we're going to do in this problem is we're going to look at the hand. And the arm, I guess, in general, and look at all the forces that are on the arm. So there it is. My sketch and translate is I'm going to draw the forearm and the hand. So I'm going to say, let's say the system is equal to the forearm plus the hand. And again, drawing diagrams in this section, it's just too hard. So what you do is you just draw a rectangle. That's what I usually do, because I don't like drawing stuff. Okay, so you get it? That's the forearm plus the hand. So this is like the hand over here. This is the arm part. Anyway, so in physics you can get away. Usually things are like circles or rectangles, because that's what I can draw. Okay, so, and I can kind of, if you wanted to remind us what this is, I guess you can feel free to draw. My red thing is those little red thingies she likes to do. So it doesn't include the ball. I guess it probably includes the thumb, but that's the system. Make sense? Okay. And then the key here is that the ball is 35 centimeters away from the elbow joint. So what I'm going to do is I'm going to define the rotation axis equals the elbow joint. It can rotate around there. So the big key thing here is this 0.35 meters from here to here. And then there's going to be other stuff like the center of mass of the arm is, the 16. This is the center of mass, the 0.16. And then there's the bicep attached. Anyway, I'm going to do a force. What I'm going to say is let's draw an extended force diagram. Because it can rotate. This is rigid body, I guess. Equals the arm. So I'm going to push this way and try to do this. So again, to draw this, I'm just going to draw this rectangle and I'm going to try to draw all the forces that are acting on it. So this is the one that I got all mixed up about before. It's the F of the ball on hand, which is equal to the mass of the ball times G. For a big, long reason I don't want to repeat. But you get it? Mass of the ball, 6 times 9.8, that's going to be that force. Just let me know if you want me to repeat that one. Every time I try to think about it, I get a little bit spinning. But that's at the 3.35. Then you've got the center of mass. Of the arm. So there's a direct gravity force on the arm there, which we can draw, which is F, I don't know what you want to call it. Anyway, it's equal to the mass of the forearm times G. Okay, so F equals mass of forearm. Okay. And then we've got another thing, which is we've got the upward force of the bicep. And then there's another force which they ask about in the problem, which it says, what is A, the force of the biceps on the forearm? This is a question mark, if that's problem A. And B, the force of the upper arm on the elbow joint. So this is what I'm going to call F sub U. And this is the upper arm force. So I guess it's being applied right at the rotation axis. So at rotation axis. So, and that's also a question mark, equals question mark. So this distance right here, it says is 5 centimeters, so that's 0.05 meters. This distance out to here is 0.16 meters, and this distance from here to here is a 0.35 meters. So what I'm going to do is I'm going to set this to be the y, this to be the x. There are no x forces. Okay. I'm going to use torque is equal to F times L times sine of theta. So theta equals 90 degrees for all these forces, for FB and the gravity and the F ball on hand. They're all acting to 90 degrees up or 90 degrees down. So sine theta equals 1. So what we're just going to do is times the forces times the distance they are from the axes. And there's actually 3 main equations, which is that the force, all the x forces sum equals 0, all the y forces sum up to be 0, and all the torques sum up to be 0. Those are the 3 equations of static equilibrium. Because the first 2 we've already done. We know it's not accelerating in the x direction. So F sub x equals 0, and this is all 0 anyways. So it's actually not a useful equation, but because there's nothing in the x direction. We also know the whole arm is not allowed to accelerate up or down. So that means that the y forces have to balance. to 0, and we also know the arm's not rotating. And so that means the torques have to balance out to 0. So these are going to be two equations that are useful. Two equations, so can solve for two unknowns. And those are F sub B, the bicep force, and F sub U, this upper arm force. Whoops, sorry. So that's my strategy. So next step is to solve and evaluate. I got a hole. Sorry, I had to push this off to the left a little. And there's that question again. What is A, the force of the biceps on the forearm, and B, the force of the upper arm on the elbow joint? So the way I'm going to do that is you've got the sum of the Y forces is equal to, well, there's the upward force of the bicep, unknown, minus the downward force of the upper arm, minus the mass of the forearm times G, minus the mass of the ball times G equals 0. So I can solve that out. I've got F sub B minus F sub U is equal to G times the mass of the forearm. I think we actually have all these plus mass of the ball. It's 9.8 times, I think it was 1.2 kilograms plus 6. I ended up that it's equal to 70.6 newtons. That's F sub B minus F sub U. So we can kind of remember that. So that's the sum of the Y forces. The next thing you can do is the sum of the torques is equal to, the upper arm is going to have a 0 torque. That's the upper arm. Because it's acting right at the rotation axis. And then the bicep, is that going to be positive or negative? It's going to rotate it up, so that's counterclockwise. So it's plus F sub B, I guess 0.05 times F sub B. And then the two gravity forces are going clockwise, so you minus the 0.16 times M sub F times G, and you minus 0.35 times M sub ball times G. And these all equal 0. So I solved that one out. I got 0.05 times the bicep. There is no upper arm, so this is going to be easy. We're just going to solve for F sub B, and then we can plug in here to solve for F sub U. Times mass of the forearm times G plus 0.35 times the mass of the ball times G. If you solve it out, the force of bicep is equal to 0.16 times 1.2 kilograms times 9.8 plus 0.35 times 6 kilograms times 9.8. Divide the whole thing by 0.05 and you get this big number. I got 449. And that's newtons. So that's the answer to A, force of the bicep. And then for B, from this star equation, you've got F sub B minus F sub U is equal to 70.6 newtons. So F sub U is equal to 449 minus 70.6. I got that it's equal to 379 newtons. Okay. And so what's interesting is that this is very large compared to the weight of the ball. And I think that is because the bicep acts, I guess, close to the rotation axis. I don't know if that's an evaluate, but. So in other words, if you're holding, I think a 6 kilogram ball is about 60 newtons. Your arm has to actually pull up with about 450 newtons to produce the 60 Newton force weight at the end of your hand. So your muscle produces this tremendous force in order to rotate your arm. And then the other weird thing is that your arm has to press downwards to keep your arm from the whole thing from just accelerating upwards. So you've got these two, you've got the Y forces have to balance and your torques. Any questions about that? That's sort of we'll do a little bit more of this when we come back from the test, static equilibrium problems, but that's pretty much your chapter 8 stuff. So next on the list is I was going to talk a bit about center of mass stuff. We talked a little bit about this. Center of mass and center of gravity happen to be the same because here on Earth, weight and mass are proportional. We had this unconstrained object on which there's no net force, rotates about a point called the center of mass, if it's out in space or something. Or if it's moving, then the center of mass follows that parabolic path. This is again from the text. How is it possible to clear the bar in a high jump if your center of mass does not reach the height of the bar? Well, it is possible if you bend your back in kind of an arch. So it's possible for the center of mass of a complicated shape to not be within the object, like a boomerang or something. If you look at the center of all that mass, it can actually be outside the object. And the simple example of that, I'll throw it to your phone here. Yeah, so there's a donut. It's making me think about dinner, but you can try to choose where the center of mass of that is. Yeah, I just think it's wherever the donut hole was. I guess they made a Timbit out of it. Right in the center there. There is an equation for it. Let me just allow this to simmer for a little bit in the background, and I'll show you a kind of a cool demo in the foreground here. So here we have a little ramp made of 2 wires, and if you put something on it, then it rolls down the ramp. Unless you put this on it and it rolls up the ramp. You see it? Rolls down the ramp, rolls up the ramp. Okay, so what that is something to do with the bevel. You can see this bevel of these train rails getting closer to one another. And so if I were to get closer, the whole thing goes up, right? And so as these get further away, the thing can go down, so it's going to roll towards where it wants to get out, right? So the center of mass is dropping and trying to find its way to the center of the Earth, even though this one goes that way, so there's that. Okay. This is how you calculate it. There's something here about grade point average, but basic idea is every object is made up of lots of little particles, and they can all have numbers on them, 1, 2, 3, 4, etc., all the way up to n. Each particle has a mass, m1, m2, m3, etc., and each particle has a position. x1 and y1 is the position of particle 1. x2 and y2 is the position of particle 2, etc. You make some big object out of that. So the way you find the center of mass is for every particle, you multiply the mass times like the x position, and you sum those products up for all the particles and divide by the total mass. That gives you sort of the weighted average of the position, the x position of all the particles. And they're kind of saying down here that if you take a y course and you get an A in it, that counts twice as much as if you take an H course, right? So, if there's a particle here which weighs twice as much or has twice the mass of another particle, then it will sort of pull the center of mass towards it because its x will count twice as much. Then you divide out by the mass. Okay? There's a much more difficult learning catalytics question coming, so let's try that. And this kind of gets into this idea. Now we're doing the y position of the center of mass. So the idea is this. You start off with an empty can of water, just with air, I guess. And then drip, 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 you allow water to go at a constant rate into the can until it fills up. And then you make a graph. The graph is a graph of position of the center of mass of the whole system, which is can plus water, versus the position of the surface of the water. So at the beginning, it starts with y water, the surface is at 0. And then you fill it up, you go along the x-axis here until you get to the height of the water is equal to h, which is the height of the whole can. So it goes from empty to full. What does the center of mass of that whole object do? One of these 5 graphs is pretty close to the answer, I think, and the other 4 are wrong. Feel free to discuss. I'll give you 2 minutes for that one. Okay, so yeah, let's see. So the idea is, I think you can think about similar limiting cases. If the can is empty, where is the center of mass of the can water system? It's in the middle. That sort of makes sense. So I think what you're thinking about with A, which is totally correct, I think this is the correct center of mass of just the water only. Okay, so that's okay. So if you answered A, I kind of get what you're thinking. I think this is probably the water only. Maybe that's kind of enough for a Monday evening. But if you think more about it, and you're thinking about the water, well, it starts at this, so it actually could be C or E. Well, that's it. It's got to be C or E. So what will happen as you fill it up? Well, as you put some water in here, like right now, the center of mass of the water is right here. And if you fill it right up, the center of mass of the water goes up. So if you think of this as 2 particles, one as being the x, I guess, or y position of the can, that's going to be right in the middle. And then you're adding to that the center of mass of the water. That's going to bring the center of mass of the system down below. The more water, it'll kind of bring it down until the center of mass of the water actually comes up, and then at the end, it'll be in the middle again. Can. Any questions about that? I think that's all. That was my explanation. Oops. No, I had one more thing I wanted to do, which is, I guess we'll go back to this. So, want to see another trick? So I've got these pieces of wood, and what I can do, let's take the top piece of wood and see how far I can push it before it falls off the end. That was it, half, right? Okay, so that's where the half comes from. So, meaning that this is something to do with gravitational torque. So you've got gravity pulling down on the center of the piece of wood. So if that's supported, like because it's on the piece of wood below it, it doesn't tip. If that goes off the end, then it tips. Gravity pulls it over. Okay? So the farthest, what I want to know is how far can I push it out? It's half. And then I'm going to leave it there and say, okay, it's stable. So now my next question is, how far can I push out these both blocks until they start to tip? So that could be as far, I don't think. That's it. Okay. And it turns out, okay, someone's already done this experiment. This one was a half, this one was a quarter. Then this one was a sixth. I'm going to put it on the actual table. And then the next one is an eighth, and then it works. And if you put another block under there, you go to a tenth. This is of, in each case, it's that much of the length of the block. And what's really interesting about this is that a half plus a quarter plus a sixth plus an eighth, this is what's adding what's called a harmonic sequence, where each number on the denominator is just plus 2 of the number before it. And harmonics sequences like that don't converge, meaning that if you add up all these numbers, you can get to infinity. So you can get as many blocks as you want. If you just keep putting them, you can have these things going like as many kilometers to the west as you want. They would all be supported by the table right over here. So, okay. North, south. Okay, so I want to do a example of that. Do we have time? Yeah, we got some time. So, example here is one block of length L is hanging off the edge of a table. How far off the edge can it go without tipping? So what I can do here, kind of know this one, it's if this distance is x, then you say that x is equal to L over 2. And what that does is that puts the center of mass of this right above the edge of the table. Center of mass above the edge of the table. So that's the easy one. What you do next, you say you have two blocks of length L. The top one is hanging a distance L over 2 off the one below it. How far off the edge can the bottom block be before the entire stack topples over? So I put this bottom one here, and I hang it over the edge some unknown amount x. And then the top one, I know, is this distance from here to here is L over 2. And then I know that this distance also from here to the center of this mass is L over 2. So what I do is I define the origin to be right over the end of the bottom block. And then I say that this x of the system, x center of mass, is equal to the x of the top times m plus x of the bottom one times m divided by m plus m. That's the equation for center of mass. But the top one is right where my origin is. So this one equals 0. So I got x is equal to 0 plus, this one's L over 2, is the bottom one, times m divided by 2m. And I get x is equal to L over 4. The m's cancel. So it's a little hard to see there, but that bottom one, I'm saying that I've defined x equals 0 to be here, so this top one has its x position in this coordinate system equal to 0. This one has L over 2, again defined away from here. So this x, the center of mass of both these objects, is going to be L over 4. If you put L over 4, then it works. And the center of mass of that system is right over the edge of the table. That's where you put the edge of the table. It's a bit tricky. And then you can, extend that to more of them. Oops, I'll just put it here, I guess. If you have 3 blocks, then what you do, once again, you put the bottom block down here. You define your origin to be right here. X equals 0, so this is x, which you're trying to compute. And then you have a whole bunch of blocks above it, maybe 2. Okay, this is mass equals 2m, 2 blocks. And by definition, their center of mass, x, their center of mass equals 0, right above the origin. So you get x is equal to 0 times 2m plus L over 2. This one is over here at L over 2. Divided by 2m plus m, and this is times m. And you get, this is 0, so you get L over 2, m's cancel, divided by 3, and you get x is equal to L over 6. And same thing, if you use 4 blocks, you get x is equal to L over 8. 5 blocks, you get x is equal to L over 10, etc. Just kind of a cool thing. So let's talk a little bit about this test tomorrow night. You're back tomorrow night. You good? And we'll scan it. As soon as I leave this room, I'll go and scan it and post it on my website. The test is tomorrow, and the room you go to is based on the first letter of your family name. The testable materials, chapters 5, 6, and 7, plus the materials from chapters 1 to 4, I guess, just due to the cumulative nature of physics. We're not really picking questions from those chapters, but I think you still sort of have to know them, if you see what I'm saying. So this is ours like when we were doing chapter 5 and upwards. And then the practicals 4 through 7, which are now, I think, are totally done. Some of you did them today, I guess. The format is exactly the same as it was for test 1. There's going to be 12 multiple choice questions with the scratch and sniff. You have to find a little star underneath each question for 2 points each, maximum. And then you have one written question where you have to do those 4 Akina steps and get 2 points for each step. Aids allowed, again, same exact rules as before. A calculator doesn't communicate with other calculators. An aid sheet you can write on both sides. An English translation dictionary, a ruler, and a nickel to scratch the scratch card. Don't forget to bring your T card, as the invigilators will be coming and collecting signatures. Let's talk about some physics that will be on the test. Maybe I'll get your attention. Because people can't hear if everyone else around them is talking anyways. So, let's talk about fuzzy dice. If you have a rear view mirror in your car and you're turning left, the fuzzy dice swings out to the right. So why is that? Well, I think it's because the whole car, including this ball, is accelerating. So this is like, it's like stationary in what you're seeing as you're turning. So you've got the wheel turned like this, you're going on the highway, and you're just slowly going around this curve, and you're just looking at that ball and it's just sitting there. But I think the ball is accelerating. So which direction is it accelerating? Yeah, so this is purely horizontal. So this one is, it's circular motion, but where's the circle? This is sort of like a banked circular motion problem. You've got a car which is turning left, so the circle you can't see. It's like you're looking down on the highway from above, and he's driving in a circle which is horizontal. It's a horizontal circle, so the direction towards the center of that circle is, it's that way. Okay? Can you picture that? The entire car is accelerating directly towards the left because of this static friction on the wheels or something like that. That's a hard one. But so there's a lot of, I guess, horizontal circular motion that you're doing. And in each case, if you're accelerating towards the center of the circle, and so it's horizontal acceleration. And then here's the question of the day, which is that if you're going to draw a force diagram of the red ball, list all the forces that you're going to draw on that red ball. It's more of a chapter 5 kind of review. You don't draw the centripetal force on the force diagram. The force diagram simply looks like this. You have the tension going along the string, you have gravity going down, and usually I write the net force off on the side. The net force is the centripetal force. It's the mv squared over r, because it's the acceleration times the mass. But that has to come from the sum of all the forces that are actually external forces acting on your object. So one more thing that I wanted to do, just for fun, is show you this. Do you remember you guys were swinging water around in your practicals and you had to do the horizontal circle? So what I was trying to get students to do, and no one took me up on this, is to swing it right over your head. So what I'm going to do is I'm going to take this cup of water, and so I'm just looking at all these great laptops in the front row. It's all good. I've done this lots of times before. I'm going to swing it around in a circle over my head and hopefully not hit the ceiling. No problem, right? Cheers. Yeah. Good luck on the test. Like I say, so actually, quick question. Why does the water stay in my coffee cup? Okay, and it's because you have gone more than this minimum speed, right? This square root G over R. In that case, the tension is pulling. It's actually hard, and you could have done this in practicals. You could have whipped it over your head. Nothing ever spills because you would have to, in order for it to fall out, you have to actually push with the string. So, like I say, I've done this a lot of times, and so far hasn't failed. It's going to fail if I crash into some of these objects. Someday it's going to get me, but it hasn't got me yet. And I will post all of those cool little hints, and good luck. I'll see you tomorrow night.